Hello everyone, welcome back to the Atharva Gate Academy. Myself Chinmay Dhaduk. In previous videos, we have completed chapter 1, that is Introduction to Strength of Material. In that chapter, we have get some basic idea about strength of material. Now in this video, we are going to start chapter 2, that is stress and strain. First of all, we are going to start with stress. I think that you will be having some basic idea about stress and strain. Now what is stress? Stress is internal resisting force per unit area. Now what is internal resisting force? Let's say we have this body and here length of the body is L. Let us take cross section area of this body is A. Here we are going to apply two equal and opposite force on this body like this. Suppose value of this load is F. Here this F load is external load applied on this body. Now we have to understand what is internal resisting force. Now understand carefully that this load F that we have applied on this body will try to deform this body, means it will try to increase the length of this body, and it will also try to break this body in two parts like this. Correct? But up to certain limit of this load, this body is going to be resist the deformation in this body, and it will also try to resist the fracture in this body by applying equal and opposite load. That load will be like this. So we can say that force is produced in this body due to externally applied load F to resist the deformation in this body, and fracture in this body is called as internal resisting force. So here these two forces are internal resisting force. So what will be the value of stress here? Value of stress will be internal resisting force, that is F, divided by area, that is A. And here this area is cross section area of this body, means this area is perpendicular to the direction of this force. Here direction of this force is this, so we will take perpendicular area. As we know that this load is normal load for this surface, or we can say any cross section of this body, so this stress will be normal stress. So we can say that stress produced by the normal load is called as normal stress, and normal stress is denoted by sigma. Now let us understand one thing, that if we have any surface like this and we have any body which we keep on this surface, here this body is allowed to move on this surface, and if we apply load in this direction, let's say having value F, so here this body will move in this direction. Means in this case this body is not going to be resist this force, means there will not be any internal resisting force produced in this body. So in this case value of sigma will be 0, means in this body value of stress, that is sigma, will be 0. So understand that although there is value of F and there is cross section area of this body A, value of stress is 0. So you have to understand that stress is not directly force divided by area, it is internal resisting force per unit area. Now while calculating the value of stress, we will take direction of this external load, we will not take direction of this internal load. Means here this load is tensile load, so we will take this value as positive, right? Now let's say we have this body which is fixed at the left hand side. Let's say length of this body is L and area of this plane, or we can say this surface 1, 2, 3, 4 is A. Now let's say we apply load F in this direction. Here this load F is parallel to this surface 1, 2, 3, 4. So in this case, what will be the value of stress? Stress will be equal to load, that is F, divided by cross sectional area, that is A. Understand that this load F is applying parallel to the surface, and we know that load which is parallel to the surface, or we can say force which is parallel to the surface, is called as shear force. So here stress due to this shear force will be shear stress. So this stress is called as shear stress, and this is the value of shear stress. As we discussed earlier, normal stress is denoted by sigma, but here shear stress is denoted by tau. So in this case, value of shear stress in this body is tau, that is F by A. Fine. Now we will see what is the unit of stress. What is stress? Stress, sigma, is equal to force divided by area. We know the unit of force. Unit of force is Newton. And what is the unit of area? Unit of area is meter square. So Newton per meter square is the SI unit of stress. Now let us take another unit in which unit of F is, let's say, Newton, and here we will take area in mm square, means millimeter square. And we know that how to convert unit Newton per meter square to Newton per mm square. 1 Newton per mm square will be equal to 10 raised to 6 Newton per meter square. Correct? And here Newton per mm square is taken as Pascal. So it can be written as 10 raised to 6 Pascal. Here this Pascal is unit of stress. And we also know that Pascal is the unit of pressure. And unit of pressure is Newton per meter square. Right? Now we know that 10 raised to 6 can be written as mega. So we can write 10 raised to 6 Pascal is equal to 1 mega Pascal. Right? Generally the value of stress is very high, so we are going to take this higher unit for defining stress. So generally we are going to take megapascal and Newton per mm square as a unit of stress. And here you can see that 1 Newton per mm square is equal to 1 megapascal. Right? If value of stress is 10 raised to 9 Newton per meter square, then it can be written as 1 gigapascal. Right? Giga means 10 raised to 9 power and Pascal means Newton per meter square. So these are the units that you have to remember for the stress. Now let us take one case. In this case we have this body which is having different cross section at different length. Let's say from this point to this point it is having cross section A1, and from this point to this point it is having cross section A2. We are going to apply two load having value F both the side of this body, and due to this load stress will be produced in this body. First of all we will find stress in this body. Let's say in this part of body value of stress is sigma 1. What will be sigma 1? Sigma 1 will be value of load F divided by cross section area at which we want to find out stress. So here our cross section area will be A1. So it is divided by A1. And now we are going to find value of stress in this part of body. Let's say here value of stress is sigma 2. So what will be sigma 2? Sigma 2 will be load F divided by area at which we want to find out stress. So here our area will be area A2. So it will be A2. Right? Now we are going to discuss type of stress. There are main two type of stress. One is normal stress and another is shear stress. We discussed that stress produced by normal load is called as normal stress and stress produced by shear load is called as shear stress. We can also say that stress in a perpendicular direction to the cross section is called as normal stress, and stress which is in the parallel direction to the cross section is called as shear stress. Now here there are two types of normal stress and shear stress. One is direct stress and another is indirect stress. In the direct normal stress, we apply axial load to the body, and due to that, normal stress produced in the body sigma is load F divided by cross section area A. Here this stress is produced by the normal load. So we can say that normal stress which is produced by the normal load is called as direct stress. I have told you that stress produced by the bending moment is normal stress. So here value of stress produced by the bending moment sigma will be m by z. Here this is the formula to finding out bending moment that we are going to discuss later on. In this case we did not apply normal load, but although there is a normal stress produced in the body due to this bending moment. So this stress is called as indirect stress, because indirectly normal stress is produced in the body. There are also two types of shear stress, direct shear stress and indirect shear stress. When we apply shear load on a body, then shear stress is produced, and that shear stress is called as direct shear stress. And I have also told you that when we apply twisting moment in the body, then shear stress is produced in the body, and value of that shear stress tau is T by Zp, that we will also discuss later on. Here we do not apply shear load, although there is shear stress produced in the body. So we can say that indirectly due to twisting moment shear stress produced in the body. So that shear stress is called as indirect shear stress. Now we are going to discuss type of stress according to direction of force. Here there are two types of stress, tensile stress and compressive stress. Here we have this body and we apply two tensile load F on this body. So when we apply tensile load on this body, tensile stress is produced in the body. In the tensile stress there are pull type of forces, right? Here you can see, and due to this pull type of forces there will be elongation in the body, means length of the body is going to be increased. And what will be the value of stress in this case? Value of stress sigma will be F divided by A. And as we know that we take tensile load as a positive, value of stress is greater than 0. In the compressive stress, we apply compressive load on the body. Here you can see that these both load are acting towards the body, means these are push type of force. These forces try to push the body, or we can say it tries to contract the body, means there will be contraction in body, and due to that length of the body will decrease. We know that value of compressive load is taken as negative. So what will be the value of sigma? Value of sigma means stress will be equal to F divided by A, and here this load F will be negative because it is compressive in nature. So value of compressive stress will be less than 0, means it will be negative. We are going to discuss type of stress, that is engineering stress and true stress, after a while. Now we are going to discuss strain. Let's say we have this body and we fix this body from the left surface. We apply tensile load P at this surface of the body. Now due to this load, length of this body is going to be increased. Let's say this length of body is L, and due to this load this body is going to be elongate. So length of this body will increase like this. And here this distance is change in length of this body. Let's say it is delta L. In this sense, if we want to find out value of stress, then how can we find out? Strain is change in dimension per unit dimension. In our case, dimension is length of this body. So what will be strain? Strain, that is denoted by epsilon, will be equal to change in dimension, means here change in length, that is delta L, divided by unit dimension, means we can say that original dimension. So divided by, there will be L. So we can also say that strain is change in dimension divided by original dimension. Or we can also say that change in dimension divided by initial dimension. So here change in length is delta L and initial length is L. So value of strain, that is denoted by epsilon, is delta L divided by L. Now here what is the unit of this strain? Unit of delta L means change in length is meter, right? And unit of length is also meter. So divided by meter. This meter will be cancelled out. So there is no unit of strain, means strain is dimensionless. In this case, we apply tensile load P. If we apply compressive load on this body, let's say it is like this, then length of this body is going to be decreased. Let's say this body is going to be contracted like this. Means this much length of body is decreased. Let's say it is delta L. In this case, if we want to find out value of strain, that is delta L by L, then we have to take value of this delta L negative. Means if it is given that length of this body is decreased 2 mm, then we have to take delta L is equal to -2. And let's say original length of this body is L is equal to 200 mm. In this case, if we want to find out value of strain, then what will be the value of strain? It will be delta L, that is -2, divided by original length or initial length, that is 200 mm. So it will be 200 here. So finally it will be -0.01. Here we have to take unit of this delta L and L same. If we take delta L in mm, then we also have to take L in mm, right? We have discussed that there are two types of stresses. One is normal stress and second is shear stress. Similarly, there are also two types of strain. One is normal strain and second one is shear strain. Strain which is produced by the normal load is called as normal strain, and strain which is produced by the shear load is called as shear strain. Now we are going to discuss normal strain. There are three types of normal strain. First is linear or longitudinal strain, second is lateral strain, and third is volumetric strain. We are going to discuss all these strain one by one, in which first of all we are going to discuss linear strain or longitudinal strain. Now let us take one body in which this is the length of this body, this is the width of the body, and this is the height of the body. Here we are going to take this direction as a x direction, this direction as a y direction, and this direction as a z direction. Let's say here we apply load in this direction. It is along length of this body, means it is along this x direction of this body, and there is also one another load in opposite direction to this. Here let's say value of this load is P. But let us consider that due to this load, change in length of this body is delta L. So in this case, what will be the value of linear strain, or we can say longitudinal strain? Here this direction means x direction is taken as linear direction, or we can say it is longitudinal direction. Strain that we have discussed earlier was linear strain, or we can say longitudinal strain. And what is the value of longitudinal strain or linear strain? It is change in dimension divided by original dimension. And here you can see that change in dimension is delta divided by original dimension or initial dimension is L. And remember this thing that dimension is taken along force. So here we apply force along the length of this body. So we are going to take change in length L divided by original length or initial length L. Here this strain is along x direction. So we can say epsilon x, that is strain in x direction, as delta L divided by L. Now if we remove this load and we apply load in y direction like this, then there will be change in height of this body. Then let's say due to this load, change in height of this body is delta h. So if we find epsilon y means strain in y direction, then it will be delta h divided by h, and it will be considered as longitudinal strain because here we take dimension in y direction in which we apply load P. So at this time this dimension is taken along the force. And now let's say we remove this load and we apply load in this direction, means in the direction of Z. I hope that you understand how we apply this load. Now due to this load, this width of the body B is going to be increased, and let's say change of this width is delta B. So in this sense, what will be the value of strain in Z direction? Strain in Z direction, that is epsilon Z, will be equal to change in dimension along the load, that is delta B, and divided by initial dimension, that is B. Here we take this dimension along the force. So this is also longitudinal strain, or we can say linear strain. Now we are going to understand lateral strain. For that we have to understand lateral dimension. Here in this case, if we apply load in this direction, then here this direction means the direction along this load is taken as linear direction, and other direction which is perpendicular to this direction is taken as lateral direction. In this case we apply load along x-axis of this body, then direction along this x-axis is taken as linear direction, and direction which is perpendicular to this direction, that is direction along y-axis, and direction along z-axis is taken as lateral direction. And similarly, dimension along linear direction of this body is taken as linear dimension, and dimension along lateral direction of this body is taken as lateral dimension. In our case, this length will be linear dimension, and this width and height of this body will be lateral dimension of this body. So now we can understand lateral strain. Lateral strain is equal to change in lateral dimension divided by initial lateral dimension. These lateral dimensions should be initial or original. Now in our case, what will be the value of lateral strain? Let's say lateral strain in y direction, epsilon y, it will be change in lateral dimension, that will be delta h divided by original lateral dimension, or we can say initial lateral dimension, that is h. Here this delta h is change in height of this body due to this load P. Generally, when we apply tensile load in x direction of this body, then length of this body will increase and width and height of the body is going to be decrease. So similarly, what is lateral strain in z direction? Lateral strain in z direction is equal to change in lateral dimension in z direction, that is delta B divided by initial lateral dimension in Z direction, that is B. Here this delta B is change in width of this body due to this load P. So I hope you understand how to find lateral strain. Now we are going to discuss volumetric strain. Volumetric strain is change in volume divided by volume, and this volume is initial volume. Now let's say again we have this same body and we apply any load on this body. Let's say due to that load, change in length of the body is delta L, change in width of the body is delta B, and change in height of the body is delta H. And let's say overall change of the volume of this body is delta V. Initial volume of this body V will be L into B into H, right? Now let's say we want to find out volumetric strain for this case. So volumetric strain, let's say it is epsilon V, it will be equal to change in volume means delta V divided by initial volume, that is V. If change in volume is given, then we can put it here, and if this volume is not given, then we can find out from here. So if we put this value here, then you will get volumetric strain epsilon V, right? Now we know that delta V by V is equal to delta L by L plus delta H by H plus delta B by B, right? And we know that delta L by L is strain in X direction plus delta H by H is strain in Y direction plus delta B by B is strain in Z direction. So we can write that volumetric strain epsilon V is equal to strain in X direction plus strain in Y direction plus strain in Z direction. You have to remember this, okay? We have discussed the normal strain. Now we are going to discuss shear strain. Strain which is produced by the shear load is called as shear strain. Now let's say we have this body and we are going to fix this body from the bottom side. Now we are going to apply load parallel to the upper surface of body, like this. This load is parallel to the surface, so it is called as shear load, right? Now due to this load P, there will be distortion of body. We know that deformation means change in dimension and distortion means change in shape. So due to this shear force, shape of this body is going to be changed. Here this body is going to be distorted like this. Due to this shear force P, this vertical surface is going to be inclined from this original place, and let us take this angle as angle gamma. So here this angle is also will be gamma. This gamma is called as angle of distortion, and value of shear strain is measured by this gamma. Means here this gamma is called as shear strain. And how to find this gamma? Let's say displacement of this point is delta, and here this length of body is L. So what will be value of tan gamma here? Tan gamma will be equal to this length, that is delta, divided by this length, that is L. Here this value of angle of distortion means gamma will be very small, and for small value of gamma we know that tan gamma is nearly equal to gamma, right? So we can write that gamma is equal to delta divided by L. So it is delta by L. So value of shear strain gamma is delta by L. And here what will be the unit of shear strain? Unit of delta, that is displacement of this point, it will be in mm, or we can say it will be in meter, and unit of this length will be in mm, or we can say it will be in meter. So here this mm will be cancel out. So this shear strain will be unitless, or we can say dimensionless. Now we are going to discuss type of stress. There are two types of stress, engineering stress and true stress. Here there is a difference between engineering stress and true stress. In engineering stress, we consider change in volume is not equal to 0, means delta V is not equal to 0. And in true stress, we consider change in volume is equal to 0, means delta V is equal to 0. Means we can also say that volume is not constant here, and here volume is constant, right? In the engineering stress, we use initial dimension, and in true stress, we use actual dimension or instantaneous dimension. This engineering stress is used in theory of elasticity, and true stress is used in theory of plasticity. Here this is the formula to find out engineering stress, sigma, and here this is the formula to find out true stress. Now let's say we have this prismatic bar. What is the meaning of prismatic bar? Bar which is having constant area throughout length is called as prismatic bar. In the prismatic bar, cross section of area may be anything. It may be circle, it may be triangle, it may be rectangle, or it may be square, but it should be constant throughout length of bar. In this case, what is the volume of this bar? Volume of bar will be A into L, area into length, right? Here this is the length of body and this will be area of body. In this prismatic bar, if we apply tensile load F both the side like this, then stress will be produced, right? And what will be the value of engineering stress in this case? Engineering stress sigma will be F divided by A. Here F is the load that we have applied on this bar, and A, that is area of this body, and that area is initial area. Understand that to find out engineering stress, we take initial area in the formula of stress. Now understand carefully that when we apply tensile load F on this bar, length of this bar is going to be increased, right? And if length of this bar is going to be increased, then area of this bar will decrease, right? Means due to this load F, length will increase and area will decrease. Let's say initial area of this body is A0 and initial length of this body is L0, and final area of this body is AF and final length of this body is LF. Now in order to find true stress, we take volume is equal to constant, right? So here initial volume will be A0 L0 and final volume will be AF LF. So it will be constant, means these both will be same. So it will be A0 L0 is equal to AF LF, right? Now what is true stress? True stress, that is denoted by sigma T, will be equal to load divided by area. And here this area will be instantaneous area, means we will take here final area, that is AF. From here we can put value of final area AF. It will be A0 L0 divided by LF. So it will be F divided by A0 L0 into LF, correct? Now here this F divided by A0 is force divided by initial area, that can be written as engineering stress sigma, right? So we can write that sigma T is equal to sigma into LF divided by L0. Here I put sigma instead of F divided by A0. Now let's say change in length of this body is delta L. So what will be final length? Final length LF can be written as initial length plus change in length, right? So from here we will put value of LF here. So it will be sigma into bracket L0 plus delta L divided by L0. Means sigma T will be equal to sigma into bracket here L0 divided by L0 will be 1 plus delta L divided by L0. And here what is delta L divided by L0? Delta L divided by L0 is change in length divided by original length, or we can say it is change in length divided by initial length. And we know that it is called as strain, that is denoted by epsilon, right? So it will be sigma into 1 plus epsilon. So finally we have formula to find out true stress, that is sigma T is equal to sigma into bracket 1 plus epsilon. Here this sigma is engineering stress that we can find out from this formula, load divided by initial area, and here this epsilon is strain, and actually it is engineering strain that we are going to discuss after a while, and value of that engineering strain is delta L divided by L0, right? So from here you have to remember this formula, sigma T is equal to sigma into 1 plus epsilon. Now we are going to discuss type of strain. There are two types of strain, engineering strain and true strain. In engineering strain we take change in volume is not equal to 0. Means here delta V is not equal to 0. Means volume is not constant. And here in the true strain change in volume is equal to 0. Means delta V is equal to 0. Means volume is constant, right? In engineering strain we take initial dimension, and in true strain we take actual dimension or instantaneous dimension. This engineering strain is used in theory of elasticity and true strain is used in theory of plasticity. Now here there is the formula to find out engineering strain. It is change in dimension divided by initial dimension. Strain that we have discussed earlier was engineering strain. So we know this formula, right? So in this case, what will be the value of this epsilon, that is engineering strain? It will be change in dimension, that is delta L, right, divided by initial dimension. Here what is the initial dimension? It is L0. So delta L by L0 will be engineering strain, and that is denoted by epsilon. Now to find out true strain you have to remember this formula. Epsilon T, that is true strain, is equal to integration of 1 upon L with respect to length, that is dl. So it is actually dl by L and integration from initial length to final length. In the notes I have taken L1 and A1 as initial dimension and L2 and A2 as final dimension. In our case we take A0 as initial dimension and AF LF as final dimension. So here our integration will be from L0 to LF. Now what will be integration of 1 upon L? It will be log L from initial length to final length. So finally it will be ln LF log final length minus log initial length, and it can be also written as ln final length divided by initial length. Here it is ln L2 by L1. Now from this equation in which volume is equal to constant, right? From here if you find LF divided by L0, then it will be A0 divided by AF, right? So we can write that ln final length divided by initial length as A0, that is initial area, divided by final area AF. Here it is ln A1 divided by A2. A1 is initial area and A2 is final area. Now we know that final length LF is equal to initial length L0 plus delta L, initial length plus change in length, right? So here if we put LF is equal to L0 plus delta L, then it will be Ln into bracket L0 plus delta L divided by L0. So it will be equal to Ln into bracket L0 divided by L0, it will be 1 plus delta L divided by L0. And we know what is delta L divided by L0? It is engineering strain epsilon, right? So here if we put epsilon instead of delta L divided by L0, then it will be Ln 1 plus epsilon, right? So finally, to find out true strain epsilon T, we can use this formula Ln 1 plus epsilon. If in the question initial length and final length is given, then we can use this formula. If initial area and final area is given, then we can use this formula. And if change in length is given and initial length is given, then we can use this formula. First of all, we will find epsilon, that is delta L divided by L0, and we will put here, then we will get true strain epsilon T, right? So I hope that you understand how to find true strain and how to find true stress. From this topic, if you will remember only formula, then also you will be able to solve question and get the answer. Now today in this video we will stop here and continue in the next video. Till then, try to understand this concept and try to understand this derivation also. And if you want this derivation, then you can write in your notes. I have not given this derivation. Okay? So we will meet in the next video. Till then, stay motivated and happy practicing.